Okay, Physics 30 is here again, Mr. T. All right, page 83. We're looking at types of curved mirrors and lenses. So two types of curved mirrors or lenses. So we've got converging mirrors, which are concave, and converging lenses, which are convex. Notice concave, convex, opposite terms. But both, of course, this mirror and this lens converge, like bring it together. Let's look at some of the basic terminology here. PA stands for the principal axis. V stands for the vertex. Okay? F stands for the focal point. C for the center of curvature. Notice that the focal length here is a positive value. Okay? So when we go to our mathematics, we're going to be using positive numbers for converging mirrors or concave mirrors. Over here, same sort of thing, except for now refraction occurs. Now O stands for the optical center. F still stands for the focal point, and the focal length is a positive value as well. Okay? Let's look at diverging mirrors. Call them convex mirrors. So when light comes and shines in, it bounces off as though it came from a point behind the mirror. That point we call a virtual focal point. Okay? But there's a focal point. Again, there's a center of curvature. There's a vertex, a principal axis, and now the focal length will be substituted in as a negative value. Okay? And diverging lenses are concave lenses. Still the same idea, right? Light refracts or bends predictably here. In other words, it spreads out as though it came from a point on this side of the lens. Okay? Light really doesn't come from here. It just refracts predictably at these two locations. Okay? We still have our optical center. This is still termed the focal length. That's the distance between the optical center and the focal point. And the focal length is given as a negative value. Let's look at spherical aberration. It says if the mirror is spherical, the parallel incident rays will not converge on the same focus. And so when these parallel rays hit the mirror, they don't reflect through this perfect focal point. Okay? The further the rays are away from the principal axis, the further they go away from the principal focus. So notice this one right here, very far away from it compared to others. Okay? A better focus is obtained by using parabolic mirrors. And of course, the same can be said with with lenses than mirrors. All right, let's take a look at images in curved mirrors and lenses. So a little bit more, there's a lot of information here, so let's just keep track of what's happening. So step one, sketch the following reflected or refracted rays. So a ray parallel to the principal axis, so comes in parallel, reflects or refracts through the focal point, or it diverges from the focal point. So notice here, right, with a concave mirror, reflects through the focal point. Here, of course, with a convex mirror, it reflects as though it came from this focal point. So it diverges from that focal point. Okay? Here we have a convex lens. You have rays come along parallel to the principal axis. They refract through and go through the focal point. And then you've got the concave lens. Notice that the rays refract outwards as though they came from F. So they diverge from F. Now, if you draw a ray through the center, it reflects back or refracts on the same path. So if a light ray comes along through this center of curvature, it'll hit the mirror and it will go back along that same path. Okay? In the case of it going through a convex lens, it goes straight through the optical center, doesn't get refracted much at all. Okay? In the case of the convex mirror, you have the ray coming in, and as though it came from that center of curvature, it reflects back out. And here, same thing. You've got a concave lens, and it goes straight through the optical center. Okay, so now the ray through the focal point reflects or refracts parallel to the principal axis. So it's similar to the first idea up here, but now the ray kind of comes and goes through the focal point and then reflects back parallel to this principal axis. That's the horizontal line right here. Same thing right here, right? Comes towards that focal point and reflects back parallel to the principal axis. And here you can see refraction occurring, but the same basic idea. So that's step one. What you do is you Draw one of these rays, either this ray here, right, the first, the second, or the third, your choice. Okay? Now you generally need at least 2 rays to be able to find out where an image is going to be located, and that's why the process is important. Step 2, locate the image. The image is always located where the reflected or refracted rays converge, which is why you need to draw more than one, or intersect. You sketch the image from the principal axis to the intersection. And step 3, you describe the image. So we can describe it based on the size, larger, smaller, or same size as the object. We can describe it based on its attitude, inverted, that means flipped vertically or upright, and type. It could be real, which is formed by real rays, or virtual. That means that a virtual ray and a real ray may intersect, such as a virtual ray would be shown here. Okay, the light doesn't actually go there, it's just a continuation of this ray. Okay, so the little summary that we have here for curved mirrors and lenses that we're going to be using. For converging mirrors, right, we have, of course, the center of curvature, but for lenses, there's no real center of curvature, so we call it 2 times the focal length. It's still a location that's important. Image characteristics and location of image. So if it's beyond C, that means it's smaller, inverted, and real. And the location of the image would be between the focal point and the center of curvature. Hold on, power went out. Here we are again. If it's on the center of curvature, then the image characteristics are the same size, inverted, and real. It's upside down. And it's on the center of curvature. Between the center of curvature and the focal point, it's larger, inverted, and real, and the image is located beyond the center of curvature. If it's on the focal point, we have no image and therefore no location. Between the focal point and the vertex, it's larger, upright, and virtual, and the location's on the other side of the mirror. For diverging mirrors lenses, where we have all locations, it's either smaller, upright, virtual, and the location of the image should be the other side of the mirror. Okay, so this is for converging. There's a lot of information with converging ones. Diverging ones are always very much the same. Okay, so in general, real images are always inverted, virtual images are always upright. Now here's the equations that we use. So we have, of course, d, they don't really define them here, but dO would be the distance that the object is from the mirror lens. Di would be the distance the image is from the mirror lens, and F is the focal length. Okay? HI refers to the height of the image, HO the height of the object, and then of course I define DI and DO then. Now we can determine the magnification by taking the ratio of the height of the image over the height of the object, or the negative of the distance the image is from the lens or mirror over the distance the object is from the lens or mirror. Notice the negative sign is because of a sign convention. Also, like the radius of curvature is 2 times the focal length. Okay, so if you notice the diagram right over here that's showing this information. Okay, so pay attention to the diagram and how it sets up, and the fact that you need, of course, they're showing 3 rays here. They're showing 1 ray that comes along, and this is like the first possibility on the previous page, and then refracts right through that focal point. Second one goes straight through the optical center and does not refract at all. And then the third one goes through the focal point on this side and then refracts parallel to this principal axis. And there's HO and HI shown, DO and DI. F, of course, our focal length. All right, here's some sign conventions. D, of course, is positive if it's real, negative if it's virtual. They're measured from the vertex or the optical center. The focal length is positive for converging mirrors lenses and negative for diverging mirrors lenses. And the height and magnification, it's positive if it's upright and negative if it's inverted, and it's measured from the principal axis, okay, either up or down. Note, if magnification is less than 1, then the image is smaller than the object. If magnification is equal to 1, then the image is the same size as the object, and if magnification is greater than 1, well, obviously the image is larger than the object. All right, I'll do a few questions on the next page. We'll draw some diagrams to start this up, okay?